You are deep into a project, switching between a dozen heavy applications, when the screen suddenly locks up. The cursor turns into a spinning wheel, and your machine grinds to a total halt. This is a crisis of physical space. Your computer's active memory, or RAM, is a finite workspace. When that workspace fills up, the system has to perform a desperate juggling act, moving active data in and out of storage just to keep the machine breathing. To see how an operating system handles this traffic jam, we can run it through a stress test. This diagram lays out our parameters. The computer has exactly 3 available memory slots, which we call frames. Approaching these frames is a specific barrage of 10 data requests. In computer science, this incoming queue is known as a reference string. The rules of the test are strict. Every time the system needs a number from that string, it checks the 3 frames. If the number is missing from those slots, the computer is forced to pause and fetch it from the hard drive. That miss is called a page fault. A page fault is the exact mechanism that causes your screen to freeze. The goal of any operating system is to intelligently guess what data to keep in its frames and what to evict, keeping that total page fault score as low as possible. Our first strategy is FIFO, first in, first out. The logic here is incredibly simple. When the frames are full, the oldest piece of data to enter the memory is the first one kicked out. Watch the frames in this initial phase. The first 3 requests, 7, 0, and 1, easily slot into the empty spaces. But because the system had to fetch them, the page fault counter instantly jumps from 0 to 3. The breaking point hits immediately when the number 2 arrives. The workspace is full. Following its rigid rule, FIFO looks at the oldest resident, ejects the 7, and slots the 2 into its place. The fault counter ticks to 4. As the gauntlet accelerates, FIFO exposes a massive blind spot. It starts evicting numbers right before they are requested again, completely ignoring how often a user actually interacts with that data. It only cares about the arrival timestamp. By the time all 10 numbers pass through the system, the frames hold 4, 2, and 3, and the final tally sits at a grand total of 9 page faults. Treating data like a rigid blind queue fails because it ignores utility. Getting rid of your most useful tool just because you bought it first is a guaranteed way to slow down your workflow. We reset the board for a smarter approach, LRU, or least recently used. Instead of tracking when data arrived, LRU actively tracks your history to make its decisions. The mechanic is highly specific. When a frame needs to be cleared, the system looks backward and evicts the specific piece of data that has gathered the most dust from a lack of use. You can see the advantage clearly midway through the sequence. In this diagram, the opacity represents idle time. The system holds 2, 0, and 1. Because the 0 was just referenced, it remains bright and active, while the 1 has faded away. When the number 3 arrives, the system has a choice. A FIFO approach would kick out the 0 because it arrived first, but LRU protects the 0. It intelligently targets the faded 1 for eviction instead. That single pivot saves a crucial cycle. When the string concludes, LRU crosses the finish line with 8 page faults. By leveraging your past habits as a predictive tool, LRU prevents the exact bottlenecks that crippled the previous run. We clear the frames one last time for the theoretical heavyweight, optimal page replacement. Optimal operates on a godlike rule. Instead of looking backward at your history, it is allowed to look forward. It can scan the incoming queue and evict the specific data that will not be needed for the longest time in the future. Operating with surgical precision, the timeline scanner darts ahead of the sequence. It dodges the exact traps that caught the other algorithms, making flawless eviction choices every single time a frame fills up. The math perfectly aligns, and the page fault counter bottoms out at 6. For this specific set of data, 6 faults is the absolute mathematical minimum. This proves a simple rule of computing. Perfect efficiency requires perfect foresight. This bar chart compares our final results. At 9 and 8 faults, the legacy methods lag behind, leaving Optimal as the undisputed victor of the gauntlet with just 6 errors. But despite winning the test in a landslide, the Optimal algorithm is entirely absent from your laptop, phone, and the servers hosting this video. The real world operates with a fatal flaw. Your operating system does not have a time machine. There is no mathematical formula capable of knowing exactly which tab, app, or file you are going to click on next. Because true clairvoyance is impossible, software engineers use the Optimal algorithm purely as a ghost. It serves as a theoretical measuring stick to test how close practical designs can get to absolute perfection. That leaves LRU as the reigning champion of the real world. By constantly updating its eviction targets based on recent activity, it reliably mirrors human behavior. In the end, software engineering relies on intelligent adaptation. When an operating system cannot predict the future, studying the immediate past remains the most effective way to keep the machine running.